Alright, so in this problem, it says that a truck carries an open container of water. The truck is constantly decelerating at 1.5 meter per second squared. Find the angle of inclination and the pressures at points A and B. And then we're also given this diagram over here. So we kind of see our stable water level, which is around 1.5 meters above the bottom of the truck. And let's try to imagine what the water would do in this scenario, right? We're slowing down. This truck is, being pushed back, if you will, like what's going to happen to the water inside. Well, I think it would kind of go, I don't want it to go all the way up there. I think it would just kind of like angle a little bit, right? Our water would not stay flat because as the fluid's in the rigid body, it still has fluid-like, actions. So when a force is being applied to it, then the fluid inside will also react. So if you kind of like hold a water bottle right next to you and then like you kind of slosh it around, you can kind of see the water flowing in that way. That's originally how I solved this problem, actually. So now that we have kind of where the water should be, since the truck is constantly decelerating, we can now find the angle of inclination. So I'm going to call this part A, not in blue, part A. And part A is to find, let's call it theta. And let's name theta as right here, this little angle. So this little angle, I'm just going to call that theta. So angle of inclination is between the original line that we got and the basically what we're thinking where the water is going to go. If it's going to rise or going to fall, the angle of inclination is still going to be the same. One will just be positive or negative, so we'll just report it positive. So we have an equation for the angle of inclination, which is the tangent of theta is equal to our acceleration in the x direction divided by gravity plus our acceleration in the z direction. What I did not write down from this problem statement is that the truck is moving in a completely horizontal way. So there's no vertical motion happening. So actually this AZ term goes to 0. So if this truck was inclined, so if I were just to grab this whole thing, I should be able to do that. And if it was going kind of up like that, then we'd have an AZ term that's just pushing us down a little bit more, or pushing us up depending on the performance of the truck. But in this case, AZ is 0. So we can just write that AX over G is equal to tangent theta. So solving for theta, we can just do the inverse tangent on both sides. So tan inverse of tangent will just give us theta. So let's just do theta is equal to tangent inverse of AX over G. So our AX, and in these kind of problems, normally X is horizontal and Z is vertical, so it would kind of look like this kind of coordinate. So we have our X and we have our Z. So that's why our AZ is 0, but our gravity is still acting downwards and our acceleration is acting backwards on the truck. So this is what's called the XZ plane, which is sometimes used in these problems. So theta, going back to that, is tangent inverse of A of X, which is, from the problem statement, 1.5 meters per second squared. And that is being divided by gravity. In this case, gravity is 9.81 meters per second squared, as we are in the metric system. So 9.81 meters per second squared. And that leaves theta to be Did I write this down anywhere? I don't believe I did, so just open up Desmos real quick. Also, Desmos.com/scientific is maybe the best thing to ever exist. So 1.5 divided by 9.81, and make sure your calculator is in degrees mode, as that's the best unit for this, which is giving us around 8.69 degrees. So what this angle is basically telling us is that the water will raise to 8.69 degrees above the horizontal. So zooming in on the truck right here, this theta, don't want to erase all that, but that is fine. Let me see if I can get that. This theta right here and this theta right here are alternate interior angles, which means both are the same in this kind of situation. So we have theta is equal to this 8.69 degrees. So now we need to find the angle, we found the angle of inclination. Now we need to find the pressures at points A and B. So let's move on to B. And we actually need to do a little bit of trigonometry here. So let's work on A first. So we're trying to find the pressure right here. And how we can do that is we can use the hydrostatic equation. So the hydrostatic equation says that there's a difference of pressure, which is equal to the density of the fluid times the gravity times h. And in some books you might see z or delta z. But that's really just the change in height. So in our case, water is our fluid, gravity is gravity, and h for point A would be from right here all the way down to right there. The thing is to find this height, we need to find this height. So we can subtract 1.5 meters, or excuse me, we can subtract this height from 1.5 meters to get this height. So let's solve for the height right on over here, because this height will also be equivalent to this height. And I'm making that claim because if we split our, see if I can get a dash line in here real quick, if we can split our truck directly in half, you can kind of see something nice happens in the fact that we now have two triangles that have 2 meters of length on each side, which add up to our 4 meters. And then we have our angles, which are the same, which means that they're basically the exact same triangles. The only thing is that for point A, to find our h, we just need to subtract this height, and for point B, we just need to add this height. So let's actually go ahead and find that angle, or excuse me, that length, which I'm just going to call O because that's our opposite. So to find the opposite, actually let me call it something else. Let me call it, no, I'll keep it as O, that's fine. So to find that, what we can do is we have a few trig functions, and I'm low-key just trying to remember exactly what it is, because we need to do, see, we have cosine, sine. Sine deals with opposite and hypotenuse, but we also have tangent, which deals with opposite over adjacent. So we could probably take tangent theta multiplied by 2. So 2 tangent of theta. So let me just see if this kind of looks correct. So 2 times that is maybe correct. That kind of looks correct. I'm getting around 0.305. So 0.305. So I'll round that up to 0.306 because it goes 5/8. So why not? And this would be in meters. And how I got this number was that tangent is equal to opposite over adjacent, right? And we're trying to find O. And what we do know is our adjacent. So if we multiply our adjacent on both sides, then we are left with A, our adjacent, times the tangent of our angle theta. And I want to make this clear, this is an O right here. These two O's are exactly the same. So our adjacent, as we split the truck in two, we have 4, which is then split in 2, so 4 over 2 is equal to 2. So that's how I got this down here, and this is our adjacent. So that's how I came up with that formula for that. So now we know our height kind of difference points. So let's work on point A. So point A. And right here, let's just do that whole delta P. Delta P is equal to rho GH. Is there any way I can highlight this? There is. That's actually kind of nice looking in the dark mode. So for point A, you just do the pressure at A is equal to the rho of water, or density of water, times gravity, times our height. And I'm going to call this height A. So this would be 1,000 kilogram per cubic meter of water multiplied by 9.81 meter per second squared, which is our gravity, and then our height. So looking back at the figure, we're over here at point A, and we're thinking that the water goes down in this as it's in the back side of the truck. So that means we can take our 1.5 meters, which is our original resting point for water, and now we can subtract this, which I'm going to now call O. So we can take our 1.5 meters, and now we can subtract 0.306 meters from that. And that should give us our pressure for point A. So do that calculation real quick. So that is 1,000 times 9.81 times 1.5 minus 0.306. And I'm going to just divide by 1,000 because that would give it in pascals, as we are in the metric system. However, kilopascals is kind of nice to display this. This would be 11.713 kilopascals. And if you don't know how to convert pascals to kilopascals, you divide by 1,000. And this is what that conversion looks like. 1 pascal is equal to 1 kilopascal over 1,000 pascals. So we can go over here, we can divide out our pascals, and then we are left with whatever it is in kilopascals. So for point B, it's almost the exact same procedure, to the point where I'm actually just going to copy all this, paste it right on down here, except instead of subtracting this, we're going to be adding. And we're going to be adding because our truck at this point is decelerating, and we are assuming that the water is kind of sloshing upwards. So as it is sloshing upwards, let me erase the answer as well, then our height will increase from this initial point. So we have our initial point of 1.5 meters, and then it will increase just a little bit of that O length that we found right over here. So just plugging this back in and doing that exact same kilopascal conversion, I'm getting 17.717 kilopascals. So this should be all of the problems complete, or all of the questions for this problem complete. So we've found our angle of incidence right here, theta. If we draw a rectangle, that would be wonderful. We found the pressure at point A and the pressure at point B on the truck. That should be the problem complete.